That's fine. All right. So you didn't exactly understand the point of this PowerPoint. Is that correct?
Yes.
Okay. So you can see my screen and everything?
Yes.
Okay. So I guess the main point of this PowerPoint is to get you accustomed to viewing data the way statisticians view data. So when, okay, an easy example to understand is, let's say you do a school activity, right? A math activity, and everyone in the class scores from one to 10, scores 6, right? That seems to be the mean. Like, you average everyone out, everyone seems to score a 6. Well, what does that mean, like in the grand scheme of things? Because the same activity done at another university, that mean over there is 8, right? And so everything is relative. Like, so if one person scores a 6 and you don't know the mean, right? You might think a 6 is pretty bad because a 6 out of 10 is 60%. But if everyone in the class is getting 5 or 6 correct, what does that 6 really mean in the grand scheme of things, in the means, right? And so statisticians view things on by standardizing them, right? So a common example is the SATs or the GREs, right? How well you do on that score is compared to basically last year's scores. So everyone who took the SATs last year, if the majority of people are scoring in a certain range, then that's the range that will be considered normal for this year's SATs. Can you give me 1 second? Sorry. So, what is it saying? So yes, okay, so standardizing scores, right? Means and standard deviations are basically standardizing scores, like the first steps of standardizing scores. And so that is the gist of this, basically, to get you to be able to understand a standardized score, to get you to understand standard deviation and visually kind of more intuitively grasp it. Now, how well you meet this objective is variable, right? And so the example that he gave, he talked about 3 types of scores that you could report: raw scores, deviation scores, and standard scores. These graphs are a little confusing, or sorry, these diagrams are here, like especially this one. This one can be a little confusing, but what it's essentially telling you is it's getting you ready for the normal distribution, right? The normal distribution table, because most of the statistics that you're going to be learning from here on out, at least until you get to more advanced statistics in grad school, will be based off of normal distribution. That means that when you get less than 5%, when your p-value is less than 5, it's saying that, yes, there is less than a 5% probability of this, like of the null being true. So the null is the state of things. So if you want to test whether cigarettes cause harm, we assume the null. We assume the simplest explanation, which is cigarettes do not cause harm. We assume that. And then you test it, I don't know, this would be very unethical, but you make people smoke cigarettes, right? Then you have a control group, you do the math, and you find that, okay, P is less than 0.05. That means there is a less than 0.05 probability of this null being true. So that's not very likely that. That means cigarettes do cause harm. But the assumption there, when you run the data, when you run the statistics, is that the data follows this normal distribution, right? And theoretically, everything follows a normal distribution if you measure enough. So if I took the heights of everyone in the world, right, it should fall under a normal distribution where the majority of people are within this height. Then there will be certain subsets of the population with extremely tall heights, a certain subset of the population with extremely short height, right? That's if I gather everyone. And if I gather maybe a specific place, like say Auburn, maybe instead of a normal distribution, I would see a lot of slant towards really tall heights, right? But that doesn't mean that everyone's heights are representative of that small, subpopulation of say Auburn. And so this is starting to describe numbers in terms of that concept. So when we say stuff like, let's just understand this right here, right? So a mean of 4 and a standard deviation of 2.19. I think, okay, I'm going to open up next week's PowerPoint because it makes more sense if you see the normal distribution table, or sorry, the graph. Let's see, normal distribution. Right here. This is what I want. Okay. So everything should fall in this normal standard distribution, right? Standard normal distribution, if you measure enough of it. And so when we say the mean is 4, that's essentially our 0. If we look at it in terms of, all right, where in this standard normal population or distribution are certain people in this data set, right? That means that when you go up 1 standard deviation or you go down 1 standard deviation, 68% of the data lies in there. So if a standard deviation is 2.19, as we have here, that means that if we add 1 standard deviation and subtract 1 standard deviation, so 4 plus 2.9, that's 6.9 or 6.19, and 4 minus 2.19. So between 1.81 and 6.19, 68% of people should be scoring in that range, right? So 68% of scores are between 1.8 and 6.19. And then as you get further and further out of this standard normal distribution, the further and further you are from the norm, I guess. So if you were 3 standard deviations above, that means 3 standard deviations would be, as each standard deviation is 2.19, so 2.19 times 3, add that to 4. So if you scored 10.57 or higher, you'd be 3 standard deviations above normal, above the mean, I guess, right? And that's really impressive because 99.74% of data lies here, right? So that means that, let's just round it up to 0.25. 0.25 will land here, or half of 0.25 will land here, half of 0.25 will land here. So like, because there's only 25% left, so they fall in these two areas outside of the normal standard distribution. So if you scored 10.57, you would score higher than 99.89% of the population. So you'd be like one of the best, if not the best. And so that is a better way of understanding data, right? So if I give you a psych test, um, for example, to measure your cognitive, I don't know, abilities, right? Well, okay, I give you a sort of training that I predict will improve your cognitive abilities. And I get a series of scores, and those that were given the training seem to score a certain amount of points, and those who weren't given the training were to score a certain amount of points. And so understanding it by the actual raw scores gets confusing because you don't know what they mean. But when you understand the standardized scores, you get, hey, whoa, the normal is, plus two, +2, -2 standard deviations. These people who receive the training are scoring like way out there, right? In the +2, +3 standard deviation range. Because if another researcher from, say, university in Spain liked my experiment, want to copy the experiment, well, okay, their base scores may be higher or lower, but that difference in the training still applies, right? And so we want to know that in standardized terms. And so that's essentially the gist of this. And he gets into how you calculate these things. So here, it's all about how you calculate the percentile of each score, I guess. So you said you did understand that part. Did you have any questions about this part of the calculations, I guess?
No, I was pretty good on the just doing the math by hand.
Hmm. Okay. Were you confused with maybe difference between deviation scores and standard scores?
Yes.
Okay. So deviation scores is still using the units of that specific data set, right? So if I were to describe it in terms of a deviation score, in this example, John scored one correct response above the class mean. The unit is still technically number of correct response, right? And so we know that he got, five correct response because we know, that's the mean. But when we go to shift to standardized scores, you don't really need to know what the mean is at all. Like it doesn't really matter what the mean is, right? Because if it was 0.456 standard deviations above the mean, we would know that it would lie somewhere. So 0.465, was that the example? 0.456, all right, 0.456. We're just going to round it up to say zero point 0.5 standard deviations, right? And so let's just imagine it's 0.5 for a second. If it's 0.5, it's right in the center here. That means, you know, that person who scored 0.45 or zero point 0.5 standard deviations above the mean, they already scored better than at least 34 plus 13 plus 2. Okay, let's just call this 34 plus 14, 48, 50. Oh, yeah. So, slow down. Sorry. 50%, of course. 50% to the left, 50% to the right. So we already know that being here in this center between 0 and 1, right, zero point 0.5 standard deviations above the mean, they've already scored better than 50% of the population. Now, if we factor in this sliver, this half, we just divide 34 in half, which is 17. So 67. That person has scored better than 60% of the population or of the data set, right? Of out of all the responses you've collected, they're like better than 67%. And so that's enough to understand what that score means, right? That's enough to understand that that score is pretty impressive. It's better than average, it's better than normal, and you wouldn't really need to know the units at all, right? So that's really the biggest difference between a standardized score and a deviation score. You switch over to, I guess, a Z unit is what it's called, a Z score, and you would no longer need to know much about the mean, you know, if that made sense at all.
So the deviation is basically comparing someone's raw score to their class, but the standard score is comparing your score to all of the classes, if that makes sense.
No, not all of the classes. Both are comparing to the class, but one is viewing it from, I guess, the percentile way that I just described, and one is just viewing it in terms of the units, right? So it's kind of like it gets better as you go down the score. Like as you go down this list right here, your description of the score gets better. You're still comparing it to the population, but it gets better. So the raw score, John scored 5 correct responses. You would think, wow, 5 correct responses, you suck. That's only half of the half of 10, right? You got half of them wrong. But with the second one, we know that he scored 1 correct response above the mean. So if the mean is 4, he scored 5. Okay, that's better than normal then. Normal is 4, he scored 5. We know that's better. So that's more information. But now, if we switch to standardized scores, we know even more information. Not only is it better than normal, it's 67%, you know, or it's, I guess, it's 0.5 standard deviation better than normal, it's 17% better than normal, and it's 67% better than everyone, right? So out of the total, data set, 60% of scores fell below what John got. And so we get more descriptive, we get more detail, more information as we go down this list and how we report the scores.
That makes more sense. Thank you.
Mm-hmm. And so this is just it's trying to show you what it looks like. So this is the standard, right? Which is the mean is 0. So just forget all the red numbers for a second. Forget these things, right? Just the standard will apply to really anything, which is mean is 0, +1, -1, +2, -2, +3, -3, right? And that in itself would cover like 99.74% of the data, right? So you really only need to know this much. You could keep going, but it just gets less and less likely that they'll fall under that category. And so now you just translate this to whatever data you're working with. So for this specific data set, the mean is 4 and the standard deviation is 2.19. So every 2.19 is equivalent to, 1 standard deviation. And so here you see him take this blue and then translate it to this red. So you're taking, or you're taking the the numbers from this data set, which is a mean of 4 and a standard deviation of 2.19, and you're translating it to this standard score. So you start off at 0, which is basically 4, but you just say 0 in standard terms. And every 1 standard deviation represents, increase of 2.19 in the score. 2 standard deviation, another increase of 2.19. If you're going negative 1 standard deviations, it basically represents minus 2.19 in the raw score, right? And this will fluctuate depending on what it is you're measuring. So if I took a bunch of measurements about weight, and the average weight was 150, and the standard deviation was 10 pounds, that means now the standard score, when we talk in standard scores, would, yeah, 0, 1, 2, 3. But if you want to know what the units mean, remember that 0, the middle, is 150 pounds, and every time you go up 1 standard deviation, you're adding 10 pounds, right? And so if a score was here, for example, and you only knew you only see a standardized graph, the standardized picture, and you're wondering, okay, this person is 1 above 0 in standard terms, but what is that number, right? Then you just have to remember the mean and standard deviations to know that number. You see what I'm saying?
Yes, that actually makes a lot more sense now that you put it that way.
Yeah. And so It's kind of training you to start, to see things in terms of standardized scores, and then it's explaining to you how to, like, I guess, just go back and forth when you want to, when you need to, I guess, for certain problems or equations. Um, but the main point is, like, get the idea that standard scores are better. Standard scores are what statisticians will use. This example, I guess, clearly demonstrates that, right? English calculus score, you would think it's, a better calculus score. Well, that's not true, because if you look at means and standard deviations, um, you if you switch over to deviation scores, you want to report it in terms of deviation scores, then it might seem like now they're equal because they're both 5 points above the mean. But that's not technically true either, because if you take into account standard deviations and you report the standard scores, you'll see that the person who scored 20 in English did significantly better than the mean because of the standard deviation. And so now we know that they have a better English score, right? Um, if you plan to take the GRE, which is a graduate exam, you'll see this, where your score in English, your score in math might be higher than it is in English, but it's in percentile rank, it's lower because everyone tends to score higher in math, right? Whereas everyone tends to score lower in English. So if you score 160 in English, 160 in math, a 160 in math might mean you're in the 55th percentile, but a 160 in English might mean you're in the 80th percentile, right? Um, and so, yeah, it's just getting you used to it. They also briefly mentioned T scores and IQ scores. Not that this would be that relevant, but certain kind of exams, certain analyses, they don't do well with negative numbers. So they want positive numbers. And so because they want positive numbers, they made the T scores. So instead of starting at 0 with a Z score, you start with 50, instead of 0. And in that way, when you go to the left, instead of calling it negative, -1, -2, you would just call it, 40, 30, 20, go by 10. And so doing that, you can have just positive numbers for certain things. I think there was an autism spectrum measure that needs it all in positives or something, in order for something to work. And so they translate to standardized T scores instead of standardized Z scores, right? IQ score, same thing, right? There are different versions of IQ tests. Certain people are given certain forms of an IQ test, but when they finally go to calculate the total, you get a score, a standardized score, right? So no matter where you are in the country, you take this set of tests that could be different for every single person, yet the score can be compared to everyone because it's been standardized, right? And I hope that help made it clearer, I guess.
Yes, that definitely makes more sense. I did not catch that with T score, like the quote 0 is 50, and with IQ score, the like quote 0 or the mean is 100 instead of just 0.
Yeah, yeah. Um, yeah. I don't know why they do this for IQ scores, but that's what they do. That's the way they chose to standardize it. The T score, there was a reason. I just don't specifically remember exactly. I just know negatives are bad, so they need the T scores for that. Normally, it doesn't matter though. Normally, like for us, a negative Z doesn't won't harm us at all. Um, and so we look at the activity. Do you have any questions about any specific